Welcome to the setup of a sample problem for Classical Physics 2, Physics 182 at Luther College. I'm Professor Jeff Wilkerson. And in class the other day, what we did was we calculated the electric field at the midpoint of some line segment that carried a charge with uniform charge density lambda. Lambda was equal to Q over L. So we did that, as you'll recall, if you were there in class, by setting up a coordinate system and adding up the vertical components. The horizontal components canceled out, and we added up the vertical components of the electric field from all these little infinitesimal charge chunks here that were dq was equal to lambda dx. As we called that the x, we called that the y, and we integrated across there. Okay? What we're going to do is we're just going to set up. I'm not going to work all the way through it because I don't feel like working all the way through it. But we're just going to set up the same problem. If we take this point and we move it out to the end of the line segment, what does this look like? And so let's try a couple of different things and just see how this works for us. And so now I'm going to move my coordinate system over here so that the line goes from 0 to L. Okay? Don't have to do that, but I'm going to do that to start with anyway and see what happens. We maybe want to move it back in the end. I don't know. But let's just see where we are. We're going to got some point P that's some distance y up here. Okay? We've still got this. All of this is still true. And we're going to integrate. We're going to say dE is equal to 1 over 4 pi epsilon naught dq over r squared. And so let's pick a point that's out here somewhere near the middle of this line segment. That's our R. And it looks like this is the E. It's got this component and it's got this component. And if we call that theta, as we did before in class, we can look at that and call that theta. Oh, it looks like, look at the magic that we have. It looks like the electric field has been refracted as it goes across the y-axis. Never mind all of that. Anyway, we got E sub y and E sub x from, it's dE sub y and dE sub x from that little charge chunklet that's out there. What we have now, by moving out here on the edge, what we have done is we've made it so that the horizontal components no longer cancel out. Every single one of the little dq's that you have as you move along here, dq, has a horizontal, has an x component of the electric field that points in negative I hat, that points in the negative x direction. Okay, so they all add up instead of canceling out. They all point that way. So you get a vertical component, a y component of the electric field that points up if q is positive, and an x component that points to the left, that points to negative x if q is positive, and you have to add all those up. So you can't do this cancellation anymore. You just simply have to do two integrals, okay? You do an integral for dE sub x and dE sub y. The integral of that is going to be the integral of this and then you will add that up to get E sub x and E sub y from this line segment. Now, we're not done here. By no means are we done at this point because we still have to pick out the components. We said in class, when we were doing the midpoint of the line segment, that the y component, the vertical component here, is going to be the adjacent with this theta right there, and that's going to give us a cosine of that theta, and this is going to give us then the sine of that theta opposite over the hypotenuse. So that's dE, this points out right there. So that's a sine of theta. So now we're going to integrate each of these from 0 to L. 0 to L, that's where our line segment in the new coordinate system. R is going to be equal to R squared, is going to be equal to x squared plus y squared. This is x as we're moving out here. Y's fixed up there. Y's a constant, just like it was at the midpoint when we did this in class. And we can look at cosine of theta. We looked at cosine of theta in class was y over r. And the sine of theta is then going to be x over r. X is not x is not varying. X is not fixed. Y is fixed. X is varying as you do your integral. As you integrate out this way, you're changing x from 0 to L. So x is going to be a variable in there. So we can write this dE sub x is equal to 1 over 4 pi epsilon naught. Let's just get rid of the dE. Let's just say E sub x is equal to 1 over 4 pi epsilon naught. dq is lambda dx. So lambda is fixed. We're going to bring that outside the integral. And that's going to be the integral from 0 to L of cosine theta over r squared dx. We have to get these in terms of x. We have to get these in terms of our integration variable now, just like we did before. And so that is going to be cosine theta is y over the square root of x squared plus y squared. And this is going to be x squared plus y squared. So we're going to end up with just what we had in class. So this looks like just what we had in class with different limits of integration out here. So this is going to be equal to lambda over 4 pi epsilon naught, the integral from 0 to L of cosine of theta was y. Y is fixed. We can bring the y out if we want to. Y's out front right there of 1 over x squared plus y squared to the 3/2 dx. And we end up with the same integral that we looked up, that we said, we could try to solve this if we wanted to do a little substitution in there. But instead we looked it up in class. And so that's our x component. We do that integral. We've got our x component of the electric field. The y component of the electric field is going to look like E sub y is equal to same sort of thing, lambda over 4 pi epsilon naught, integral from 0 to L. But what's up on top now? Everything else looks the same except we have an x up on top instead of y that we had up on top before. X squared plus y squared to the 3/2 dx. Now we can look that one up too. That's actually a little bit easier integral to solve. That one's not terribly hard to solve. But we could just do a u substitution here. Say u is equal to x squared plus y squared, and du is equal to 2x dx in that case. And so then we've got a 1 over u to the 3/2 du with some constant 1/2 out there floating around. So we can do this. But now we have two expressions. So we solve this equation to get the electric field y component. We solve this equation to get the electric field x component. And we can, when we're done, we can write the strength of the electric field plus some angle that the electric field makes with the vertical axis, or we could write it just in component form, E sub x times I hat plus E sub y, E sub y times j hat, and we'd be in good shape right there. You might need to remember, if we do it that way, however we do this, you might need to remember that this is pointing in the negative x direction. We've kind of we've kind of hidden that in the way we've defined cosine theta and sine theta up through here. We've kind of hidden the fact that this is actually pointing in the negative direction, and you might just need to remember that and drag that along and stick that in. So this looks like, look back at what we did in class for the midpoint, for the electric field at the midpoint of a line segment of charge, and now we slide that point from the midpoint out to the end and see how this is different and see if this makes sense to you. So that's what we got for you here today. We might do another problem or two in the next day or two and post them. Have a good day, everybody.